Good day, ladies and gentlemen. We are welcome to our lecture number 1 on Cmen843, which is semiconductor microelectronics. As I know, all of us already learned something about semiconductors because it is the basis of electronics engineering. But nevertheless, we are going to take some few moments to revise the fundamentals of the course for better understanding of what we should learn in this course. In the first place, we know that the elements we have in chemistry, they are placed or they are arranged in what we call a periodic table or periodic chart. And this periodic table has groups ranging from group 1 to group 8. So those elements that are in the left hand side, that is group 1, 2, 3, they are basically metals. And those elements that are at the other end, that is from the right hand side, 8, 7 and what have you, they are categorized as non-metals. And between these two extremes, we have what we call semiconductors, and basically they are group 4 elements. And we know that silicon and germanium are the most common semiconductor devices of group 4. And we should also need to remember that germanium was the first semiconductor that was commercialized and was used from the invention, but later the volume of usage of silicon has become the more popular against the silicon. And we know the matter exists in 3 different states. We have solids, we have liquid, and we have gases. So these semiconductor elements, they are solid in nature, and that is why we call them solid state semiconductor electronics. And any solid, the atoms or the molecules are arranged in what we call a crystalline structure, and in that respect we have what we call lattice parameter. This lattice parameter is just a distance, average distance between one atom and the next, or maybe between one molecule and the next. So the lattice parameters for silicon and germanium are 0.543 nanometer, that is for silicon, and 0.556 nanometer for a germanium. And apart from these elemental semiconductors of group 4, we also have compound semiconductors, and the most commercially used is gallium arsenide. It is a compound containing gallium and arsenate, and if you combine the two, it will give you gallium arsenide. And also, apart from this gallium arsenide, we have other compound semiconductors like indium phosphide, like gallium nitride. They are also of significance because they are being used in a large quantity. This gallium arsenide, the indium phosphide, the gallium nitride, and the indium antimonide, and of course aluminum arsenide, they are semiconductors which are formed by combining group 3 elements and group 5 elements. So if you look at it, they are like sharing the atoms in such a way that 3 plus 5 will give us 8, and each one is using 4. Just it is behaving like silicon and germanium, which have 4 electrons in their valence shell. We also have other classes of compound semiconductors, which is made from group 2 elements and group 6 elements. A typical example here is cadmium selenide, which is a compound semiconductor from group 2 element, which is cadmium, and group 6, which is selenium. So these materials, we call them compound because they contain more than one element serving as semiconductors. And also, if we look at group 4, you find that carbon is also a group 4 element, but in most cases we don't use it as a semiconductor. The reason is simply because the binding energy of carbon is very high, in such a way that it normally behaves as insulator. And also if you have a cubic boron nitride, which is a compound, like silicon carbide, all of them are compounds. At normal temperature, they have high resistance, so they work as an insulators. But whenever the temperature starts rising, the molecules binded will get an extra energy and the bonds will start breaking, and if that happens, they will start working as semiconductors. Now let us look at the electronic structure of crystals, because I told you any element which is in solid state, it is arranged in what we call a crystalline structure. So if we look at the crystalline structure of a silicon, we'll see that the silicon has a electronic configuration that maybe if we come here, we have the silicon is is number 14 element, which means its atomic number is 14. And if we can remember our electronic configuration, this is the typical electronic configuration of silicon, where we have 1s carrying 2 electrons, 2s carrying 2, 2p carrying 6, and 3s carrying 2, and 3p also carrying 2. So we can see that the valence electrons, the 4 of them, they are in 3s and 4s. So that is why here we have 3s and 4s, each carrying 2 electrons. And now these electrons, when arranged, they will be in the outermost shell, and they are the valence electron. And each of these has 4 valence electron, so it will be forming a bond, that is covalent bond, with 4 neighboring atoms. So in this way, it will share one with each of the neighboring atoms in such a way that they will now form what we call a covalent bond. So if you say 4 times 4 will give you a total of 16 valence electrons for this covalent bond. And as I said, when we are at the room temperature, they are all binded and they are in the valence shell, which means there is no mobile electron. But whenever we put an extra energy, maybe thermal energy, electrical energy, or even photo energy, light, there is every tendency that these covalent bonded electrons can have extra energy and jump into the conduction band. And this Eg we are seeing here is the amount of energy that we need to break the covalent bonds of silicon in such a way that the electrons will now be mobile. They will be in what? Conduction band. We have already discussed about this. And also the band orbitals of entire crystal, that is the arrangement of molecules in a solid, they are delocalized. What we mean by this delocalization is that the electrons in the first silicon and the 4 neighbor silicons, they don't belong to any one, but they belong to all the binded atoms that form that covalent bonding. And as we have seen from the diagram before, the conduction band, it can be regarded as a linear combination of all the antibonding orbitals. What we mean by antibonding orbitals is those electrons in the outermost shells that can easily break and become mobile. So, and I told you from this diagram that we need to apply an energy Eg, which is enough to break these bonds so that the electrons can now be delocalized and they will be mobile. And the electronic structure is a possible appearance of energy gap. What we mean by this statement is that whenever the electronic structure of bonded elements, especially the covalent bonding, which is weaker compared to electronic bonding where there is complete transfer of electrons, but in the covalent they are what? Sharing the electrons. So it gives ability that whenever this amount of energy, Eg, which is energy gap, is applied, it can easily break from the covalent bond and become mobile. And whenever it becomes mobile, we say it is in conduction band. The size of this energy gap is dependent on the binding energy. I told you the covalent bonding and electronic bonding or electrovalent bonding, they are different. The electrovalent bonding is very strong because we don't have complete transfer of electron, but yes, we have complete electron transfer. For instance, if you have sodium chloride, for instance, sodium is group 1 element and chlorine is group 7 element. That extra electron in the outermost shell of sodium can easily be transferred to the to the chlorine, so that we have a complete transfer. That is why the bonds are very strong. But in covalent bonding, the elements are not transferring electrons completely to the others, but rather they are sharing in such a way that all the shared electrons belong to all of them. So in this way, it is very much easier for the bond to be broken. So the binding energy of the type of bonding, whether electrovalent or covalent, depends the amount of what this energy gap. If you look at insulating materials, the gap is very, very large. Therefore, it is not possible for those materials to release electrons from the valence bond into the conduction band in such a way that it can conduct electricity. Typical examples of insulators we know, they are plastic, rubbers, and glass, and what have you. And in conductors, you see that, like metallic bonding, the outermost electrons, they are free to move. They are not stationary in the valence bond, so they move completely from one atom to another. So in this case, already we have electrons in the conduction band. Therefore, the valence band and the conduction band, they overlap one another. By overlapping, it means the energy gap doesn't exist. So even at room temperature, as we know, the metals conduct electricity, and of course they conduct heat. So on the other hand, in between the insulators and the conductors, we have what we call semiconductors. And the pure form of semiconductors, as everybody knows, is called the intrinsic. The unpure one, where we adopt an extra or an external element into it, we call them extrinsic semiconductors. So for these pure semiconductors, you see that the energy gap exists, but it is very much smaller compared to that of insulator. So for this reason, if you apply a very small amount of energy, it can break the bonds and electrons will start moving. And in such a way, we call them, they were in valence band, but now they are in what? Conduction band, by application of a small amount of energy. So now, if we look at the bands of intrinsic semiconductors, we have already seen that silicon and the germanium, they are the most common, and they were the initial semiconductors that we have used, isn't it? So this silicon and germanium, we call them indirect band gap semiconductors. But if you go to the compounds where you have more than one element, like gallium arsenide, like indium phosphide, and many others we have just discussed, so they are called direct band semiconductors. So now, what we need to know is, what is the difference between the direct band and indirect band semiconductors? Now, if we look at the direct band semiconductors, we call them with this name because the electron is promoted from the valence band into the conduction band directly without change in momentum. Everybody supposed to know a momentum is the product of what? Of what? Mass and velocity. What this is saying is that even small amount of energy is enough to break the bonds in direct band gap semiconductors. There is no need of change in momentum. But if we look at the indirect, it means for you to move electron from the valence band into the conduction band, there is need of what? Change in the momentum of that arrangement. And a typical example of the change that does not involve change in momentum is by absorption of photon. Photon, we know it is what? Light. That is, even small amount of light energy can break bonds in direct band semiconductors like gallium arsenide, and we know that amount of light, is very it contains very small amount of energy. So why is it that in the direct band we don't need any change in momentum? The reason is that we have what we call favorable alignment, favorable shape of the energy bands in the direct band semiconductors like gallium arsenide. Okay, so the difference between the direct and the indirect band semiconductors, if you are talking of normal electronics, is of very small importance because it is not that very necessary. But when you want to design electronics components or electronic systems which are operating in optoelectronics sense, that is, they operate using light. For instance, we have light dependent resistor, we have light dependent transistor, we have light dependent diodes, and what have you. So if you want to design those optoelectronic systems, now the difference between the two is very, very important, because in this case we don't use the indirect that requires change in momentum, but rather we use the direct one, which does not require any amount of change in momentum. The amount of light, very small amount of light, can move electron from the valence band into the conduction band. Now electronics in crystalline solids, they need to satisfy one law, and that law is what we call Pauli exclusion principle. And what does this principle say? So the principle is now telling us that if we ignore any effect of the energy from the light photon or from the thermal energy heat, the valence band of a semiconductor is expected to be completely filled, meaning all the valence electrons are in the valence band, while the conduction band is assumed to be completely empty, if we make the assumption that there is no any change of energy due to light or due to thermal source. So in this case, it means the conductivity of a pure semiconductor should be very, very low, because all the valence electrons are not mobile. They are in the valence shell, while in the conduction band we don't have any electron. So for this, we can assume that the conductivity is very small, or even zero, if the Pauli exclusion principle is satisfied. But whenever there is increase in the energy of the semiconductors, either from light or from the heat, you find that the conductivity will start increasing when that energy is used to move electrons from the conduction valence band into the conduction band. So at ordinary temperature, that is room temperature, about 25 degrees Celsius, a pure semiconductors of some electrons will be moved to the conduction band because we have some energy. 25 degrees Celsius definitely carry some heat energy. If you want to eliminate any heat energy, you have to go to absolute zero temperature, which is 0 degrees Celsius or minus 273 degree Kelvin. So when we are at room temperature, we have a little bit of energy, and that energy will start breaking the bonds in such a way that electrons in valence band should now move into the conduction band. And if we want to express the thermal equilibrium for the electron system in any solid state semiconductor, we use a formula that we call it Fermi-Dirac distribution function, which is given as f of E equal to 1 over 1 plus exponential E minus EF all over KT. We know that this E, or first of all the f of E, is the probability that we have an electron in a particular state, that is, whether the electron is in the valence shell or in the conduction band. And the electron state, conduction band or valence band, there are only two options. If the electron is not in its valence band, definitely it should be in what? Conduction band, and vice versa. So for this, you can see that we have how many possibilities? Only two. One valence band, the other one conduction band. So what is the probability for electron to be in the valence band is 1 over 2. And the probability for the electron to be in the conduction band when the bonds are broken is also equal to 1 over 2. So therefore, the probability is exactly 1/2, 1 over 2. So the occupation probability for the holes, because wherever electron is missing, we know that that place, the vacancy where the electron has been removed, we call it a hole. So the probability for existence of a hole at a particular place it means is that the electron has already left that place, and the formula for that is F subscript H of minus E, which is the negative of what? The electron, and is equal to 1 minus the probability for the existence of the electron from the formula we have just seen here. Okay, so now by convention it means the whole energy is definitely the negative of what? The electron energy. Let me come back here. Here we have exponential E minus EF, and when we take the negative of that, it will be EF minus E. Okay, so whenever the temperature of the semiconductor is finite, meaning it has a certain value, it is not up to infinity, the band is nearly, I mean the valence band is nearly full, which means all the electrons or majority of the electrons are expected to be in the valence band. And if we assume that, it means the conduction band is nearly empty. Okay, so this Fermi energy, the formula we have just seen, must fall somewhere in between the band gap. That is exactly 50%, just as we discussed on this formula. So we can assume that the absolute value of E minus EF, it should be greater, much greater than what? KT. You know, K is what? Boltzmann's constant, and T is the absolute temperature in Kelvin. And if we make this assumption, we can simplify these expressions by neglecting our one. For instance, here, if we say this one is very, very much greater than KT, so it means this minus this will give you something close to infinity, and exponential infinity is also around infinity, so which means this value is much, much greater than 1. So we can easily do away with the 1 with that assumption. And if you do that, your expressions for that, for probability for electron should be this, and probability for the hole should be this. Somebody need to ask me, why is this? Because if this one goes, we have 1 over this, and 1 over this, if you can remember your mathematics indices, laws of indices, when you say 1 over something is equal to that 10 raised to power minus 1. So this is why our f of E, if we make that assumption and 1 is neglected, the expression should be here, see the minus here, and that for the whole should be here also, see the minus. So if we now assume that EC is the energy at the bottom of the conduction band, and EV is the energy at the top of the valence band, then the difference between EC minus EV will give us that our EG, which is the energy gap. If you want to understand this, let's look at this diagram. You see the distance between the valence band to the conduction band is what we call our energy gap. And if we want to find that energy, we are not going to take it from the top of the conduction band, no, from the bottom of the conduction band to the what? Top of the valence band. That is what that expression means. The difference between EC, that is the energy at the bottom of the conduction band, minus EV, the energy at the top of the valence band, is going to give us our energy gap, which is EG. Now, so the concentration, we can have an expression for the concentration of electrons at the conduction band, and the formula is given by this, N is equal to NC exponential that. We have seen this expression already. And the concentration of the holes at the top of the what? Conduction valence band should be given by this P. P stand for the holes, N stand for what? The electrons. Is equal to NV exponential that also. Now the NC capital and NV, they are what we call the effective electron concentration at the bottom of the conduction band, or the concentration of the hole at the top of what? The valence band under conditions of full occupancy. Now these values we have seen, the small n for the electrons and small p for the holes, it is independent of the Fermi energy, that is EE. While somebody will say, no, from this expression EF is here and EF is also here, but we are going to see how we eliminate them, and we now see they are independent of that expression. Now, how do we eliminate that EF, which is the Fermi energy? We will multiply N by P, and if you do that, N times P is equal to NV NC exponential this. Why do we have this? Let me go back here. If you multiply exponential and exponential, you take 1 and add the values on top. So you can see that here I have minus EC plus EF. So if we add it to this, we have plus EV minus EF. Here is plus EF, here is minus EF. So they will cancel out. At the end of the day, I will be left with EC minus EV. And if you wish, this one, we have already the difference between the two. We define it as our energy gap, that is EG. So my expression now can be written as this, where minus EG or EG stand for the difference between the energy in the conduction band and the energy in the valence band. And if you look at this expression, as we have already said, it is independent of this Fermi energy because EF has already gone, and the band gap energy is just a characteristic property of the semiconductor material we are using, meaning this EG for silicon is different from that of germanium, is different from gallium arsenide, indium phosphide, and all the examples we have seen. It is depending on a particular semiconductor we are dealing with. So for this reason, the carrier concentration in the semiconductor, they will constitute what we call mass action equilibrium. What is the mass action equilibrium saying? The mass action equilibrium is saying the products of semiconductor electrons and the holes at low temperature is supposed to be approximately equal to the product of the one that is doped when the temperature has risen. And for this reason, if we wish, instead of using N for electrons or P for holes, we can just say let's multiply these two, that is NP. Instead of saying NP, I will say NI squared, because N is represented by Ni, P is also represented by Ni. So if you say N times P is the same thing as Ni times Ni, which will give you what? Ni squared. So the expression will now become this. Just we replace NP with what? Ni squared. We call this Ni the intrinsic concentration of either holes or electrons, and it only depends on the absolute temperature if you look at it, because NV and NC, they are normal and fixed concentrations, and K is Boltzmann's constant, and EG, I told you, is a characteristic of the material we are using. The EG for silicon remains the same forever, that of germanium and that of all other things. The only thing that changes here is what? The temperature. Whenever the temperature changes, this intrinsic concentration can also change. So far it has been, we assume that this Fermi energy level must fall between the center, because we have already seen that we have only two options, either to have an electron in a place or to have a hole there. And we said, since they are true, the probability of finding electron is 1/2, likewise that of the hole. So this Fermi probability should be somewhere between the center. And this diagram now can help us understand this, because we assume this is our conduction band and this is our valence band, and we assume that probability for finding either electron or hole between the two should be in between the amount of energy gap required. Okay, and if we want to prove this, we can just assume that in intrinsic case, the concentration of holes is equal to concentration of what? Electrons. So we can say N is equal to P. If you do that, we are equating these two. This is for the small n and this is for the small p. So if you take the natural log of both sides, take the natural log of this, take the natural log of this. You know, the natural log of this will end up giving you log NC plus log of this. And we know exponential and the natural log cancel. And here we have log NV plus log of this, because the log times E will cancel out. If you do that, you will finally arrive at this formula, meaning EF, this Fermi energy, is equal to half of what? Energy in the conduction band plus the energy in the valence band. And if we assume this parameter is not here, we can say that it is already halfway, but there is a slight difference, and that difference is given by this formula. I have KT ln of NV minus NC. If you look at K is constant, NV is constant, NC is also constant. The only variable here is what? The temperature. And by analysis, it has been expressed, or it has been proven that this difference is just around 1%. Meaning, if the EF is not equal to 50%, it can only be around 51%. Also, the difference is not much. Okay, so now if you make an analogy of this analysis with the crystal bonding, the band gap energy, that is the EG in a semiconductor, is simply corresponding to the covalent bonding energy, the amount of energy that is required to hold all the electrons together. So if you want to break them, you have to apply an energy that is a bit greater than that binding energy. So the band gap should always exist within any crystalline solid, as we have seen, since the stability of that system requires what we call the binding energy. For you to make any electron move, you have to overcome that binding energy, and that is why you apply energy EG. So the band gap energy is just a difference of minimum conduction band, that is EC, and the maximum valence band, which is EV. If we say minimum, we mean the bottom of the conduction band, and if we say maximum, we mean the top of the valence band. And I believe we have already talked about this. So ladies and gentlemen, as I said, today's class is just a revision of what we're supposed to have learned during our undergraduate days for semiconductor electronics. So thank you very much. I advise you to watch this over and over again and try to understand it. I believe if you can watch it many times, it will be clearer to you. And also, in case if you have any problem, if you have anything that you want to get more information about, you can contact me through the group, and of course my mobile number is also accessible there. Thank you very much, and this is our first class. We'll meet in the second class. Thank you.